Hello boys and girls, so in this video we are going to continue with our discussion on topic 8. We have 8.4 Interference of reflected light in thin film. What is a thin film? A thin film is a thin layer of material that has a different index of refractions than its surrounding. For example, we might have a soap bubble. So the soap is the thin film whereby the A outside and inside of the bubble is A. Or we might have an oil spill on the water. So the thin film will be our oil. So, light will reflect from the upper and lower surfaces of a thin film, and they will come together in the eye at a certain point, and they will undergo interference. Thin film interference is responsible for all the color that appear in soap bubble and also oil slick. That's why we will observe that a soap bubble will have multicolor. The multicolor actually is due to the interference of the reflected light. So class, in order to understand the interference of thin film, we need to understand what is meant by occurrence of phase change upon refractions. So when light wave undergoes reflections, phase change occurs as follows. When light travels through a material with smaller refractive index towards the material with larger refractive index, for example, A to gasoline, the refracted ray will undergo pi radian phase change that is equivalent to 1/2 of a wavelength. Okay, for example, as shown in the animation below, observe what happened to the wave when it strikes on the boundary of the two medium. See, this is our reflected ray is being inverted. Tengok, sampai sini dia diterbalikkan. Okay, so crest sampai sini dia jadi trough. This is what we means by the reflected ray undergoes pi radian phase change. Alright, so if this is my incident wave, you will notice that upon reflections from the denser medium, the ray have been inverted. So, yang crest akan jadi trough. Yang trough akan jadi crest. So, dia diterbalikkan. So, they undergoes pi radian phase change. Alright? But when light travel from a larger refractive index towards a smaller refractive index medium, for example from glass to A, we will find out that there is no phase change upon reflections at the boundary. Okay, let us observe the movement of this wave. See, when it reflected, that doesn't have anything happen. Okay, bila dipantul balik, dia sama macam yang datang. So, datang macam crash, pantul balik pun crash. There will be no phase change if the reflected ray is being reflected from a smaller refractive index or less dense medium. Clear? So you will notice that the incident wave and the reflected ray, the reflected wave is the same. There will be no phase change upon reflections. So now let us check our understanding on the phase change upon reflections. So, is there any phase change upon reflections for ray 1 and ray 2? Okay, let us take one of this figure and we try to solve it together. So, let us focus on figure B. Okay, if we refer to figure B, ray 1 is being reflected at these positions. Ray 2 is being reflected here. So, for ray 1, we will notice that for ray 1, there will be no phase change. Why? Because this ray 1 is reflected from a less dense medium. 1.3 is less than 1.5, so there will be no phase change for ray 1. What about ray 2? So if you notice, ray 2 is being reflected here. Okay, so ray 2 is reflected from 1.4 denser medium compared to 1.3 less dense medium. So ray 2 is reflected from a denser medium, so there will be pi phase change for ray 2. Okay, so ini adalah cara kita tentukan sama ada reflected ray kita mengalami phase change upon reflection ke tidak. So, apa you perlu buat? You just compare, sebab cahaya kita gerak dari atas pergi ke bawah. So, you just compare nilai refractive index atas dengan yang bawah. Kalau yang ni denser, less dense, so no phase change. Kalau sini less than, denser, so there is a phase change for ray 2. Jelas? Alright, so you might try on your own after you finish this video for figure A and figure C. Then we continue. So class, how actually interference occurs for a thin film? So, we refer to this figure. We have a thin film, gasoline, float on water. So, when monochromatic light, single wavelength, strike the film nearly perpendicular to the normal incident, we have an incident light. It strikes now nearly perpendicular to the surface of the thin film. What happened? At the top surface of the film, reflections will occur and produces light wave represented by ray 1. Okay, so it will be reflected, forming ray 1 at the top surface of the thin film. However, refractions also occurs. So some of the light will enter the thin film, some of the light will enter the thin film, and part of this light is reflected from the bottom surface of the film and passes back up through the film, eventually re-entering the A. So we have a second light wave which is represented by ray 2. So we have two reflected rays. Moreover, we will find out that ray 2 having traversed the film twice and travel farther than ray 1. If we compare to ray 1, ray 2 travel farther. So, because of the extra travel distance, there can be an interference between the two reflected waves. If constructive interference occurs, then an observer who detect the superposition of wave 1 and wave 2, they would see a uniform bright film. But if a disruptive interference occurs, an observer would see a uniform dark film. So, whether we see a bright film or dark film, it depends whether constructive or disruptive interference occurs for the both reflected ray. So this is how interference occurs in the thin film. So the interference in the thin film is due to the superpositions of two reflected rays. One reflects from the top surface of the film, another one is reflected from the bottom surface of the film. So class, basically, if you want to write the condition of constructive and destructive that occurs in the thin film, we have to take two factors into considerations. First one, we have to consider the optical path difference between the two reflected rays. Before this, we already state that ray 2 travel an extra optical distance of 2 nt compared to ray 1. So ray 2 will travel down the thickness of the film and then it's being reflected at the bottom of the thin film and travel back upward. So it travels an extra distance of 2 nt. N is the refractive index of the thin film. T is the thickness of the thin film. The second factors that we need to take into consideration is the occurrence of phase change upon refractions. So class, remember, when light travels from less dense medium towards a denser medium, it will undergo a pi radian phase change upon refractions. So this is the two factors that we need to take into consideration when we deal with the interference in thin film. For example, thin film 1, reflected light with no phase difference. So let's see, we have a thin film of 1.5. The thickness of the thin film is denoted by T. So there will be two reflected rays. I denote it by ray 1 and ray 2. So you will find out that light is partially reflected at the upper and lower surfaces of the thin film, forming reflected ray, ray 1 and ray 2. Ray 1 will undergo a pi phase change. Same goes for ray 2 will also experience a pi phase change. Let us check whether it's correct or not. So observe, ray 1 is reflected here. So it's being reflected when ray travel from less than to denser medium. So they experience pi phase change. Ray 2 is reflected at point C. Ray 2 is reflected at point C when it travels from less than towards denser medium. So ray 2 also have pi radian phase change. So when we compare these two reflected rays, there will be no phase difference between them. Why? Because both of them experience pi radian phase change. So both reflected rays, they will act as in-phase coherent source, and when they meet at a point, they will produce interference pattern. Then class, point D are very close to point B because we said the light is incident almost normally. So BC and CD might become straight line. Thus, we might say that ray 2 travel approximately 2 nt further compared to ray 1. Why 2 nt? Satu thickness pergi ke bawah, lepas tu satu thickness naik ke atas. So 2 nt. Kita kena darab dengan N. Kenapa kena darab dengan refractive index? Sebab the speed of light dalam medium yang berbeza adalah berbeza. That's why kita kena darabkan 2 kali thickness tu dengan refractive index thin film tu. Alright? Jelas, ha? So, since our reflected ray is in-phase coherent source, in order to have constructive interference, our path difference between the two reflected rays, 2 nt, must equal to m lambda. And in order to obtain a destructive interference, the path difference between the two reflected rays, 2 nt, must equal to m plus half lambda. So the m represents the order number that always start from 0, 1, 2, 3, and so forth. So class, we are going to find out that the minimum non-zero thickness of the thin film, they will satisfy the condition for destructive interference. That's why sometimes we also know this type of thin film as non-reflective coating. Non-reflective coating. Because why we call it as non-reflective coating? Because we find out that for that minimum non-zero thickness, they specify destructive interference. Okay, they specify destructive interference. Then class, we have another type of thin film whereby the reflected light have a phase difference of pi radian. For example, this one. I have the thin film of thickness T. The refractive index of the thin film is 1.33. Above and below the thin film is A, for example. So, light will be partially reflected at the upper surface of the thin film, forming refracted ray 1, and the lower surface of the thin film, forming reflected ray 2. So, reflected ray 1 will experience pi radian phase change because is being reflected when it travels from less than to denser medium. But then, for reflected ray 2, there will be no phase change for reflected ray 2. Why? Because when ray 2 reflects at point C, it's being reflected when it's traveled from denser to less dense medium. So it's being reflected from a less dense medium, so there will be no phase change. So if we compare the two reflected rays, we will find out that these two reflected rays will have a phase difference of, these have pi phase change, this one have no phase change, so pi minus 0, you get pi radian. So there is a phase difference of pi radian between these two reflected rays. So both reflected rays will now act as anti-phase coherent source. So when they meet at a point, they will produce interference pattern. So again, at normal incident, we will find out that point D is very close to point B. So B, C and CD might become a straight line. So our ray 2 will travel approximately 2 nt further compared to ray 1. So class, for constructive interference to occur, our path difference between the two reflected rays, 2 nt, will equal to m plus half lambda. And in order for the destructive interference to occur, our path difference between the two reflected rays, 2 nt must equal to m lambda, whereby the m represents the order number. So for this kind of thin film, we find out that the minimum non-zero thickness for the thin film will satisfy the constructive interference. So due to the constructive interference, so we might get a very strong reflected ray. So this kind of thin film, we also call it as reflective coating. Okay, we call it as reflective coating because it satisfies constructive interference for the minimum non-zero thickness. So class, let us summarize what we have in thin film interference. So we might have different layers for a thin film. So the condition for constructive and destructive might be different. It depends on whether the reflected light have a phase difference of pi or they have no phase difference between the two reflected light. Okay, so it depends on our reflected light is antiphase or in phase. If antiphase, then the equation to obtain constructive will be 2 nt equal to m plus half lambda. Destructive will be 2 nt equal to m lambda. But if our reflected light is acting as in phase coherent source, then in order to get destructive, our 2nt is m plus half lambda lah. Our disruptive is 2nt equal to m lambda. Then how we are going to know that our refracted ray is doing constructive interference or destructive interference? Macam mana kita nak tahu? Dalam satu situasi yang diberi tu, cahaya yang dipantulkan, reflected light tu, dia mengalami constructive ke destructive interference? So kita cari keywords dia. So keywords that indicates constructive interference is like strongly reflected, appear clearly seen, being observed, bright. So kalau you nampak keywords ni, so itu memberitahu kita reflected light kita melakukan constructive interference. What about destructive interference? So keywords that indicates destructive interference is like non-reflective, missing, unseen, no light is found, dark. So if you see all these keywords, then you know that one. So if you see all these keywords, then you understood that the reflected light is doing destructive interference. Clear? Alright. So class, on the next video, I'm going to show you how we are going to apply the equations we have in interference of thin film. So see you on next video.